The topic of this screencast is the standard free energy for micelle formation. So in other words, if we start off with a bunch of surfactants floating around in solution and they form a micelle, what is the standard free energy change for that? So we'll start finding the process in terms of a chemical reaction, or in this case, more of a process. So we have a certain number of surfactant molecules. We know that the aggregation number N naught is the number of molecules in a micelle. We take that many surfactant molecules and they can undergo the process of forming a micelle. Let's write out micelle. And we could write the reaction this way, or we could divide through by the number of molecules in the micelle. So we're going to divide through by N naught. And we say S is the concentration of surfactant molecules. And if we had one surfactant molecule, that will form 1 N naught of a micelle. So that'll be the reaction that we're going to analyze. So let's choose this one. So K equilibrium is going to be the activity of products over the activity of reactants. So we've got the activity of micelles to the 1 over N naught all over the activity of surfactant. And typically we are going to assume ideal behavior. If we assume ideal behavior, we can say we've got the concentration of micelles to the 1 over N naught all over the concentration of surfactant. And that is a little arrow here, assuming ideal behavior. And if we don't want to assume ideal behavior, we can use activity coefficients. But for now, we're just going to assume ideal behavior. And we had better put little subscripts here to indicate this equation is only true at equilibrium. So this quantity on the right is only equal to K equilibrium when we've reached equilibrium. Okay, so we'll rewrite that on the next page. Once we have this equation, we can remember that delta G standard for this process, in this case for micelle formation, so let's write delta G mic standard is equal to negative RT log of K equilibrium. So we can just plug in our expression for K and say delta G standard for this process, micelle formation, or negative RT log, and then we just plug in our expression for K equilibrium. So it's the concentration of micelles at equilibrium to the 1 over N naught all over the concentration of surfactant at equilibrium. All right, so we can split this up. Since this is a logarithm, we can split this into pieces, and we can say delta G standard for micelle formation is equal to negative RT. We can use the property of logarithms that if we take the logarithm of something to an exponent, we can bring the exponent in front of the logarithm. So we can have 1 over N naught log of concentration of micelles. And since this is on the bottom, we know that's going to be the negative logarithm concentration of surfactant at equilibrium. So we'll put the equilibrium there. Okay, so when we look at this, since we've got a sum, or in this case a difference, we know that there might be that one of these is way bigger than the others, and we can neglect the smaller one. Well, we know the concentration of micelles is going to be much, much smaller than the concentration of surfactants because it takes so many surfactants to make a single micelle. So this term is already smaller than this term, and we're dividing by the aggregation number. And typically for surfactants, this N naught is going to be around 50 or 60. So that means this term is much, much smaller than this term. So we're going to neglect this term and simplify and say delta G standard for micelle formation is just going to be negative RT times negative log of concentration of surfactant at equilibrium. What is the concentration of surfactant at equilibrium? Well, we know that that is going to be equal to the CMC, the critical micelle concentration. So we can just plug this in here, cancel these negative signs, and we get our final equation that delta G for micelle formation standard is just going to be RT log of the CMC. And the only assumption we've made there is that this term is much bigger than this term and that we have ideal behavior. If we didn't want to have ideal behavior, we could just plug in the concentration of surfactant at the CMC times the activity coefficient. So let's do an example. The delta G standard for sodium dodecyl sulfate in water at room temperature. So we need to look up the CMC. Under those conditions, the CMC is about 8 millimolar. Okay, now whenever a standard Gibbs energy is referred to, we have to specify the standard state. This is really critical because if we look at our equation, we said delta G standard for micelle formation is equal to RT log of the CMC. Well, we could express the CMC in any concentration units we wanted, and of course we're going to get a different numerical answer for our delta G standard depending on which units we use. So whenever you see standard free energy changes, those numbers are meaningless unless you know the standard state. So make sure, for instance, if you're comparing the propensity of two different surfactants to form micelles, you would, and you're using the delta G standard, you need to know which standard state. Okay, so let's go ahead and say that we're going to be using the practical standard state. So the practical standard state is a 1 molar standard state. Okay, so now that we know that, we can just plug in our numbers. We have to switch the concentration to the appropriate standard state. So R 8.314 joules per mole per Kelvin. We said we're working at 298 kelvins. And we couldn't just plug in the concentration in millimolar because we're using a 1 molar standard state. So we convert to molar units. And when we do that, we end up with delta G standard for micelle formation for this particular surfactant is negative 12 kilojoules per mole. You may, in the literature, occasionally find that this surfactant has a tabulated delta G standard of micelle formation at negative 22 kilojoules per mole. That's using a Raoultian standard state, which is putting the concentration in terms of mole fraction. So as an exercise, you should convert this concentration from molarity to mole fraction and verify that the delta G standard that results is negative 22 kilojoules per mole.